Start recording now.
Go team. Well, it gives me great pleasure to introduce Matthew, who I unfortunately never had in class. But I've worked with him the past, I think 10, 9, 12 months, 9 months, whatever. And he'll give you more insight about that. But I knew Matthew and was very excited to work with him when he came into my office, as he will share. But specifically just because he's such a fantastic contribution, or such a fantastic part of the department. He's worked in the chemistry stockroom for a summer. He's been very active in our ACS at Lawrence, ASCL. And he is just an overall fantastic student. And when you get to explain something, or you're talking about a chemical concept, or in many cases, he was talking about a biochemistry concept, and I was like, oh, how does that work? But as soon as one of us met a moment where we didn't understand, we both had that, what, oh, wait. And then we'd explain, and then it was like this wonderful just moment of realization, and then the excitement continued, and then you kept diving deeper. And so he's been incredibly inspiring to work with. And we would have been presenting this work at the ACS meeting in Philadelphia, which is close to home for him. He's from Pennsylvania. Anyway, but soon we will present this at some point in the future, I promise. Anyway, so without further ado, I give you Matthew.
All right, thank you, Allison, for that introduction. Hello, everybody. Welcome to my presentation on the exploration of green chemistry concepts in natural dyes and design of a laboratory activity for non-chemistry majors. Thank you all for being here. I'm going to start from the beginning, from before I even knew that I was going to be doing this. Oh, and my keys aren't working. That's a great. Sorry. Okay, cool. So our story begins with a visit to Allison's office, as Allison just said. So over the course of last summer, I was thinking about what faculty member I wanted to do my capstone presentation, work with. And having never talked to Allison before, really, but knowing that she's a pretty cool person because I've been around the chem department for quite a while. I wanted to see if I could do some work with her and, get to know her better. And so I went to her office and told her that I was really into green chemistry at the time, and my idea for my capstone project was to redesign an organic chemistry lab in the hopes of reducing the amount of hazardous waste that the chemistry department produces. And she really liked this plan. She thought that that was a great idea. And unfortunately, since I hadn't taken any physical chemistry, she was like, yeah, I can't really let you do work in my lab, but I would totally do your original idea. So I was like, okay, great. Nice to meet you. See you later. And carried on with my life. A few days later, she reached out and is our wonderful lab supervisor. And he said that actually the lab that creates the most hazardous waste in the chemistry department is the dye and textile lab that she does for her class called Chemistry of Art. And so she was like, do you want to just redesign this lab for me? And I was like, yeah, that sounds really cool. I mean, I don't know anything about dyes and textiles, but yeah. And so that was it. So to frame, the rest of the talk will be framed around this lab activity. So I'm going to explain what it's about. So I only was changing the method. First is the most important point to make. All the theory behind it was going to be pretty much the same, or that was the goal. So students would start out with this multi-fiber sample, which you can see has 6 different strips here. Oh, why is it? I didn't touch anything. And each of these strips was a different textile. So this one might be wool, this one might be cotton, this one might be polyester, etc. And so the students were asked to take vibrational spectrum of each of the different strips using IR. And this was mainly just to show them that they were in fact different from each other, because, you know, it's important to test what people. But the main pull of the lab was to examine how the textiles, because all of these things are different, and how they would interact with dyes. So they were put into four, well, more, but originally 4 different dye baths, ranging from crystal violet to Congo red, to see what the affinity was like for each dye to each kind of textile. So this gets into a little bit what the theory behind the lab is. The theory behind the lab is intermolecular interactions, so hydrogen bonding or London dispersion forces, etc. Basically, how would the textile interact with the dye molecule in such a way that the dye molecule will stick to the textile? And so they would dye in each of these different dye baths, and then they would also take one of these multi-fiber samples and dye it with alizarin as a point of reference, and then they would take one of these samples and put it in a mordant and then dye it with alizarin to see what effect the mordant would have. And all of their data and results were basically just observations to see what they could observe and what they could take away from those observations and make conclusions about what was happening at the molecular level between the textiles and the dye molecules. So some of you may be saying, okay, well, why change anything? It seems like a perfectly fine lab to me. And I want to point out again that Daniel Demers was saying that this is the lab that creates the most amount of hazardous waste. And the reason for that is because synthetic dyes are generally not very good for anything living, nonetheless humans. So there's this hazardous element, and there's also quite a large quantity of waste that comes along with that. Because the dye baths are literally tubs of dye, you had to kind of try to process all of this waste. And that was both time-consuming and difficult. Additionally, working with synthetic dyes is not very nice. One such dye is crystal violet, which exhibits carcinogenic properties, and so why create an unnecessary hazard to the students who will work with this? So I look toward a solution in natural dyes. Natural dyes might not necessarily reduce the quantity of waste being produced, but it will render it benign, or at least that was the goal. Benign meaning that it would not be hazardous and it should have little to no negative effect. This brings me to the concept of green chemistry. So let's start with just what is green chemistry? Green chemistry was come up, like this was just a brain like child of a guy who was a brilliant chemist by the name of John Warner. And he wrote a book about it in which he defines green chemistry as the utilization of a set of principles that reduces or eliminates the use or generation of hazardous substances in the design, manufacture, and application of chemical products. And I really want you to focus on just the utilization of this set of principles that he talks about, because that set of principles are also known as the 12 principles of green chemistry, which kind of serve as a how-to and like a guide for practicing green chemistry. So here they are. You'll notice that, hopefully, after looking over quite a few of these, that it's a pretty broad area. So we have everything from like preventing waste, which is kind of along the lines of what I'm doing, to designing for energy efficiency, to real-time pollution prevention. And authors are not afraid to put green chemistry in the titles of their papers if they even only use one of these things. So they could only have, used a method that used safer solvents or something, and call it a green method, which just makes green chemistry that much more broad, which can be a good thing. But to give you some examples of the products of green chemistry, we have things such as biodegradable plastics. That's a great thing. Non-toxic cleaning agents, or like pesticides that don't persist in the environment, which helps soil health, or even the use of natural dyes, which I have strongly hinted is where I'm going with this. So now that you know kind of what the lab activity involves and what green chemistry has to say, I want to talk to you more about why I wanted to move away from synthetic dyes. And so let's start with, what is a synthetic dye? Synthetic dyes are man-made, pure and simple. They're often found to be quite bad for living things because of their toxicity. Like I said, crystal violet is pretty carcinogenic and not really something you want to be working with. The reason synthetic dyes are used is because the dye industry sees them as being very efficient and effective. They have like pretty decent results, and you can just make the dye and then use it. Like there's no need to like do a whole complicated extraction, which is why natural dyes, that's their drawback. So the major leg up that natural dyes have over synthetic dyes is they are very sustainable. It's not nearly as like energy intensive, time consuming, or costly to use natural dyes as opposed to synthetic dyes. And often natural dyes are less hazardous than synthetic dyes, in terms of green chemistry. Then there's a lot more reason to use natural dyes. So I thought this is a great visual image in case it's not quite clear yet why synthetic dyes, like what the difference is. So this image on the left has been dyed using synthetic dye. And you'll notice that the color is quite brighter, and the colors on the right are much like softer. This on the right has been dyed with natural dye. And the reason that industry doesn't like using natural dye, again, is because besides from having to extract it, they probably could find a way to synthesize it, but like they don't want to have to just extract it. They also, natural dyes don't show more variability in terms of what textiles they bind to. They don't necessarily bind to every textile that you want. And although synthetic dyes don't necessarily do that either, they definitely bind more of them. So you get kind of more bang for your buck with synthetic dye. And so there's this kind of issue of quality control of there's too much variability with natural dye, so synthetic dye is the safer option. And because industry uses it, is reflected in the original lab activity. Okay, excuse me. So I've now covered the dyes and why we use them, and kind of, excuse me. And now I'm going to talk about the textile types, because although I didn't change anything about the textile, it's still important to show what was there in the original lab activity. So you'll notice that my crude drawing from before doesn't really do this justice, but this has been dyed. And I've labeled each of these strips with the corresponding type of textile. So, oh my gosh. So the textiles are all polymers. And this is important to remember because each of these units or monomers will bind differently to the dye molecule because they're all different. Some of you more astute ones may notice that these are fairly similar. They only differ in this acetate group, but as we can see from this dyed sample, that matters because cotton here is dyed and acetate is not. This is the color that is just there before you dye it, even though both of these are cellulose. This is cellulose acetate, this is just cellulose. So it's important just to emphasize that, to show the other side of the thing that the dye is binding to. Okay, so I find pictures super helpful. This is an example that I drew. Oh my goodness. My mouse is touchy, I apologize. This is wool. This molecule in blue is wool. This molecule in red is a dye molecule. And these bonds in pink are hydrogen bonding interactions between this OH group on the dye molecule and this ketone and a hydrogen between the wool and the dye molecule. I would like you to imagine that since this is only a monomer of wool, that it extends off in a chain on each of these in this direction. Monomer means that it's a repeating unit. So this unit will repeat. If you copy paste this whole thing and just like stick it here, it'll just go off on this chain. And so because there are other groups on this chain that can interact with these groups, there are other groups here on the dye molecule that it can interact with and form more hydrogen bonds. And so even though these hydrogen bonds are weak, when there are more of them holding this dye molecule together, it makes the interaction slightly stronger and can hold the dye in place. Okay, so now we're on to mordants. So I've covered dyes and why we use them and how they interact with textile fibers, or at least one of them. And hopefully you've got that it's important to understand what the molecular structures are, because then you can understand how the interaction can happen. So let's start with what is a mordant. A mordant is a dye fixative that binds dye molecules by creating a coordination complex between the dye and the textile. And again, a picture here will be quite helpful. So in reference to the last slide, this is now, imagine that this is like the wool molecule, but it's just lines. And then this is a dye molecule. Well, it is a dye molecule, don't imagine that part. And this is an aluminum mordant. So a mordant is basically a linker between the textile and the dye molecule. And instead of creating weak hydrogen bonding interactions between the molecules, it creates stronger coordinative bonds between the metal and between the metal and the dye molecule and the metal and the textile. Coordinative bonds, because they're stronger, allow several important side effects. They can extend the length of time that the dye stays attached, and they can also affect the color. So on the left here is a sample that has not been mordanted, and on the right is a sample that has been mordanted. So the difference is obvious, and they come quite in handy. Often, mordants will accompany a natural dye for the reason of changing the color, because natural dyes, like I mentioned before, don't dye very brightly. So often mordants can be used to help increase the intensity of the color. So my first goal in moving on to now what I did was to select a natural dye source. And I came across a great one, red cabbage. And the first thing that struck me about it is that we eat it, which seems kind of silly, but that means that it's probably not going to hurt me. If I can ingest it, it will be fine. The second thing that I found is that it has a pretty simple dye extraction method, which that's great. If students can do it, that's the point. The third thing is that it's extremely efficient, or extremely cheap, excuse me, and it's pretty readily available. You can just go to the grocery store and buy a head of cabbage, and there you go. The fourth thing that I hadn't really anticipated, but I was pleasantly surprised to find out, was that it's a natural pH indicator. And I'll say more on that in a second. These green symbols around here are the green chemistry principles that I took into account when choosing this dye, or like that were resulted from choosing this dye. So why is red cabbage a natural pH indicator? Hopefully you understand that pH indicator indicates pH. And so the reason for that is if we look at the dye molecule, this molecule here in the center, cyanidin, is the molecule that causes cabbage to have that purpley reddish color. And it's also, coincidentally, not at all, the chromophore, or the dye molecule. All of these terms are the same. At a neutral pH, this is what it looks like. As soon as we lower the pH, or in other words, add a higher, more like increase the concentration of protons, we change the structure. Because we've added this proton here, we also have a positive charge, overall charge on the molecule. And when we lower the pH, or raise the pH and decrease the concentration of protons, we ended up removing a proton from the molecule, which results in a overall negative charge on the molecule because we now have more electrons than protons. So this, these are just fun pictures, but they also illustrate exactly what I was just talking about. This one on the right is at a neutral pH. So in water, there's no change in color. This is exactly what it looks like when you just have it. But as soon as you add acid, we see that we have a red color. And then when we add base, we get this greenish blue color. Please excuse the textile in there, but we see this color change. And that's pretty interesting. Shout out to Cabbage Merchant over here, for those of you who are waiting for that. And so the really fun thing is it's not like as you add acid, you get a color, then you add base and you get a color. It's a whole spectrum of color as you increase acidity or you increase base acidity. And this is probably my favorite picture that, yes, I did take from this whole project. So again, lower pH, we get reds. Higher pH, we get greens, and everything in between is just like, this is a difference of 1 pH, and look at that color difference. Like, color is so fun. And so observing this is good. It'd be nice to have some data to go with it that would say, yes, this is in fact what we observe. And to get such data, the instrument that can give us that data will give it to us in absorption. So it'll shoot some light through one of these vials, a bunch of different wavelengths, and it'll tell me which wavelength one of these vials absorbs at. And so before we get into that data, I need to talk about absorption versus reflection. So everything we see falls in here, this visible light range, which is actually not very much, but you know. So all the colors that we see have an associated value in nanometers, and these are all called wavelengths. So we see red at about 740 or so, and we see violet at about 400 nanometers. So how does this help us? Well, since the instrument will only record those values in nanometers that the sample absorbs, it won't help us in terms of what we see, because what we see is the reflected light. And so again, I'm going to turn to an example. There's a nifty tool to help us with this thing called this absorption reflection thing called the color wheel. And the example that I'm going to use is imagine a green leaf. That's it. Yeah. So chlorophyll, that's this hunker of a molecule right here, absorbs all the red light. And since orange and purple both have components of red in them, we won't really see very much of them because, again, the chlorophyll will absorb that light. What we will see is the light that's reflected, that is not absorbed, which consists of yellow, green, and blue light. Well, yellow and blue light combine to make green light. So we see green. Voila. How cool is that? So applying this same principle, this is the data, this is our curve, and I have color coded this so that the data, this curve, will match the color that we observe. And the observed color will be over here on the left. The x-axis is wavelength in nanometers, and the y-axis is absorbance. Up here, I have a visible light spectrum with the chromophore in the place where, roughly centered on the place where we see the absorbance peak. So this little hill is called a peak, and that indicates the place. The top of the peak indicates the place where we get the absorption value. So this, for example, this one is about at 530 nanometers, which is pretty solidly in the green. I don't really need to know that, I guess. Pretty solidly in the green. And since all of the green light is being absorbed by this molecule, we are left to see red light. The red light is the one that's being reflected, and that is indeed what we see. At a pH of 5, oh yeah, that was a pH of 3. So at a pH of 5, we see that this hill is shifted slightly more to the right. So we see that it absorbs at about maybe like 550 nanometers. Well, maybe like 540. It's pretty close. And although it's close, it's not as red as we can see. And so does this make sense? Yes, it's not quite as much green. It's kind of a mix of green and yellow. And the complementary colors of green and yellow are red and purple. And so the mix of red and purple give us pink, pretty much. Next one we see is purple. So again, this is probably more around 560 nanometers. And we see that we're pretty much on the edge between green and yellow here. So opposite yellow is purple. And since we don't really have as much green, the purple will kind of dominate whatever is left of the red that we would see. And so that's why we see purple. So we're on track so far. We're doing great. At a pH of 7, we absorb pretty much in about 605 nanometers or so. And that's pretty solidly in the orange, while the complementary color to orange is blue. And again, that is exactly what we see. So we're still on track. At a pH of 9, this peak is so close to the last peak that you just saw but it has to have been shifted slightly more to the right, even by maybe like 10 nanometers or something, because we don't see blue anymore, we see green. So we're probably right on the edge between orange and red, which would complementarily give us a green bluish. And so this doesn't look very blue to me, but I suppose the green wins out a little bit, and so that's why we see green. So this is all of the compiled slides that you just saw on one graph. And the reason I have this in here is to point out that all of these peaks are single peaks, meaning you don't see it go up and do like 2 humps and then come back down. It's like 1 hump. And this is significant because it tells us that there's only one dye molecule. I had not read anything about the chromophore previous to doing this experiment, and so this was super valuable information. If, for example, we had 2 different molecules that absorbed at different wavelengths, which then corresponded to 2 different reflecting wavelengths, and then we only observe one color, you can think of this as you have blue paint and yellow paint, and you mix it together to get green paint. Like there's 2 components, there's not 2 components. The single peak tells us that there's only one molecule providing the color, and then that molecule shifts along as we change pH to absorb at different wavelengths to produce color, which is kind of significant. Okay, so this is the end of my bit of experimentation that I did on the dyeing. I didn't think that I would have to do this when I first started this project, but since there was a mordant that was introduced to me during the beginning, I was like, okay, well, let's see if we can find a greener mordant. The original mordant that was used was aluminum potassium sulfate. And unfortunately, aluminum is a neurotoxin. So that's not great to work with. So let's not use that. Instead, I found a mordant called iron 2 sulfate, which besides looking very pretty, is pretty cool because you can, after using it, you can remove it from solution by adding base, which will make it precipitate out. It'll make it become solid again, and then you can dispose of it in a more quantitative manner and get rid of the solution that it had been in, just as if it was cabbage juice. You know, like you could just put cabbage juice down the drain. It makes waste much easier. So the next 3 slides are going to be my results of mordanting and dyeing together. And most of this is just visual. It's not at all, there's no more numerical data. So this is 3 textile samples in increasing concentration from least mordant concentration at the bottom to highest concentration of mordant at the top. You'll note the color difference. What was interesting for me was that I thought perhaps that the mordant might convince, all of these are dyed with red cabbage, by the way. So I thought that red cabbage might be having like that the chromophore might have more of a affinity. Might have more of an affinity for these. Where'd my mouse go? For these ones that aren't dyed, if they were first treated by a mordant, and this obviously shows that that's not the case. What is happening? I didn't touch anything. Okay, sorry. So that's data set number 1, I guess. The second thing that is worth mentioning is these 2 textile samples are dyed under the same conditions, same mordant concentration, Same pH, yet we see two different colors. These are pretty much the same, but these two textiles, I believe this is polyamide and this is cotton, do not look the same at all. And I have no explanation for this. Either I'm really bad in my ability to make reproducible results, or this is another thing that the industry worries about when using natural dyes, is that we don't have very good reproducibility at all. And so more exploration, excuse me, really needs to be done to figure out why this happens. And lastly, these were all dyed, excuse me, with no mordant at various pH. So pH is increasing from right to left. If these help you more, that's great. So on the left here, we have a pH at a pH of about 10. We see greens, and that's what you would see. You would see green cabbage juice, a green solution on. It was dyed with green, like it wasn't a different color than what you see on the textile sample. This was dyed at a pH of 7, and this was dyed at a pH of 5. This was 3, and it's good color variation is what we're seeing. And we're also seeing that it's consistent across all of these, that these three, for whatever reason, these two and this one down at the bottom, just cabbage does not like them. So what have I done? Because I've showed you a lot of pictures. So I have replaced the synthetic dyes from the original activity with red cabbage. Red cabbage, because it's so colorful, don't need to find other natural dyes, at least at this point. So go team. Additionally, the waste produced from using red cabbage is benign, meaning I don't need to worry about what effects it might have. You can just dump it in your grass and your grass won't die, which is a good sign. Not that that should be the standard, but you know. I also replaced the mordant with a more sustainable one, aluminum potassium sulfate to iron 2 sulfate. You will recall this image from a few slides ago. And the takeaway from this is that the waste being produced can be handled in a safer way and not have any negative effect on anything, really. As you saw, I got fairly decent dye results. There's a bit of a hiccup with that quality control issue, but fairly good dyeing results. It dyes fairly well. And so using all of this so far, I rewrote the lab activity to include basically just the method. The theory could stay pretty much the same, but I could also now include this new section about pH, given that red cabbage is a pH indicator. And so this means that this lab activity will be used to teach future students at LU, which I think is pretty cool. Something that I didn't really expect, oh, that's not true, wait a second, that I should know, that's what I meant to say. Something I should note is that since this lab had been the greatest producer of hazardous waste in the department, now has nearly zero hazardous waste, with the exception of that solid iron 2 sulfate. And so that feels really good, and like I can be proud of this. So what does the future look like? Because, you know, should talk about that. Great question. Anybody interested in green chemistry stuff? I am so sure that there are plenty of projects waiting within the chemistry department. As I learned, all you have to do is go ask, and you shall receive. No, I'm just kidding. But yeah, no, sky's the limit, and use your imagination. So I'd like to say thank you to, firstly, to Allison for being so enthusiastic and engaging with me throughout this whole project. I don't really know if I can really say how much thanks I feel in words, but I really couldn't have asked for anything better. To Deanna and Graham for leading me and the other chemistry seniors in the senior seminar and pushing us to be the best we can, even during a pandemic. Your guidance was really, really appreciated. To DMART, my gosh, there's so much to thank you for. Everything from providing me the materials I needed to answering the questions that I didn't really think through all the way, aka dumb questions, to offering to let me use part of my stockroom shift to work on this project. You've been really supportive every step of the way, and so thank you for that. And to my peers and friends, thank you for all of your past and continued feedback and support. I feel extremely lucky to be part of such a wonderful group of people. And here are my references, and I will take questions.
Yay. Sorry, my internet is quite crappy today, so.
That's okay, as long as I didn't cut out.
Questions?
Ooh, I have a question.
Yes.
So in the original lab, did you see the same thing where those 3 different textiles didn't take any dye? Or do you think that has something to do with the cabbage?
That is a great question. I have never done the original lab. I have only read it. So I don't think so, but I could refer to, I think that it's only a cabbage thing, but I will first, okay, there you go. In case you couldn't see, Allison is holding up a thing, and that is not just a cabbage thing.
Cool, thank you.
Excellent, good question.
What was your favorite part of your project?
Ooh. My gosh, probably all of the colors that I got to see. That was, I can't stress enough how cool I was to see, add a little bit of base or a little bit of acid and just see all of these different colors in a row. That was so cool.
When we're thinking about the difference between synthetic dyes and natural dyes, is there a difference in the stability of them over time? Like how long the dye stays on the textile?
That's a great question. I honestly don't know enough about, I haven't studied, I've really only focused on cabbage natural dye. So you mean stability in terms of how long, how well it binds, the affinity?
Yeah, if a company was thinking of trying to dye a piece of clothing or something with cabbage compared to a synthetic dye, if the clothing would become less vibrant over time more quickly with the cabbage compared to the synthetic dye.
Yeah, okay. Yeah, no, that's a great question. My guess would be that there's probably, because industry has a lot of researchability, so I would guess that they've probably figured out what chromophores can bind more strongly to textiles versus cabbage dyes. Do you want to jump in, Stefan?
Would you agree that we need to be awful careful when we're drawing a hard line between natural and synthetic? As
absolutely.
One being good and one being bad.
Oh, absolutely. I did not mean to offend you at all. if I did, but
it's I know this is my job to say, but as chemists, our job is to accurately convey risk. And so
sure.
I think it's something we can.
Sure.
I think
so. Sorry.
Cabbage dye is no doubt safer than most red dyes that we've done, but that information is hard fought.
Sure, absolutely. Yeah, I should clarify that by natural and synthetic, I only meant the realm of, in a very general sense.
Sure.
Yeah.
Do you
Frankly.
think,
Or Victor. Go ahead, Victor.
okay, so do you think the new natural dye, which Cabbage is more economically efficient than the original dye?
Not at all. Not at all. Industry will definitely prefer synthetic dye because those dyes can dye across a much greater, it can dye much more different textiles, generally speaking, again, and you can get better colors than you can and reproducibility than with natural dye, than with cabbage.
Frankly?
Can you go over more of the procedure of how you got the dye from the cabbage?
Yeah, I boiled it, basically. That was pretty much it.
Any other questions? If not, I would think let's give our speaker another round of applause. And I thank you all for joining us today, and I hope to see you tomorrow or Friday. If you want to hang out and ask Matthew any other questions, we can be here for a few more minutes before I have to go off to my next Zoom meeting. Otherwise, I will see you later.
Yay!
Subscribe, Matthew.
Thanks.
Yay!
Thanks.
That's the most colorful projects I've ever seen.
Wait, Matthew, I have another question.
Yeah.
Do you think it's feasible to be able to mix your cabbage dye that you've made with other natural dyes to try to get different colors?
Yeah, probably.
Okay.
I would say so.
Think about turmeric. And are you like turmeric?
Oh, yeah, you could, for sure.
Okay.
Mm-hmm.
Go team.
Go team.
Great job.
Thanks.
Matthew.
Oh, thanks, Larissa. Okay.
Yay.
Okay.
Bye.
Bye. Larissa or Maria, do you have a question?
Bye,
I'm trying
Matthew.
to figure out how to leave.
Okay.
Using my phone this time.
Good job.
Thanks.
Team. Well done. Well done.
Go team.
I'm actually teaching I just did a video this morning on the dyes and stuff, and I was like, oh my God. And I showed a video of just the cabbage changing color that I found online. I'm like, it's awesome. So,
Yeah. Okay.
well done.
Cool. Thank you.
Check it off. Good job.
Yes.
Okay. Thanks.
Although so since you've got your presentation done, if you can go ahead and send it to me,
Yeah.
that'd be fantastic.
Okay. I will right now.
Sure. No pressure. I'm gonna test some slides today.
Yeah, sure. No problem.
Allison's like, yes, pressure. I need it now.
Thank you.
Okay. Again,
Bye.
Good job. Go enjoy.
Okay. Thanks. Bye.
How are you?
Oh goodness, I am.
Oh, wait, let me stop recording.
Oh,